Okay, I think we can start. So, welcome to Walter Gavira's PhD defense. So, Walter, you have 55 minutes to talk about your thesis.
Well, hello everybody. First, my thesis is titled Modular Vector Fields for Lattice Polarized K3 Surfaces. And well, there's an outline of what we're trying to talk about. First, some informal consideration about the problem, the previous works or attempts to solve these problems, our results that solve partially part of our proposed problem, and what's a method. And then the method basically contains two parts, one algebraic part and a transcendental part, and I'll proceed to explain both of them. First, the problem. Well, as it is known, the Eisenstein series E4 and E6 generate the modular elliptic forms. And what happens with the E2? That Eisenstein series is not a modular form, it's a quasi-modular form. So it gives an extension of the notion of modular form to quasi-modular form. We would like to attempt, we would like to construct a generalization of Siegel modular form to quasi-modular form similar to this extension. So our problem is to try to construct Siegel quasi-modular forms. The previous works were, well, the first reference I found was due to Movasati in 2013. And in that part, he mentioned the existence, one way to construct Siegel quasi-modular forms. He developed the transcendental part, or I'm calling here the transcendental part, but the algebraic part, which involves studying a certain moduli space, and in particular, some algebraic vector fields defined. It was not done. It was later done, maybe mainly in two papers, one by Fonseca that studies this in a much broader framework. It allows to study even its stack structure, that moduli space that was missing in the first reference, and in Movasati for the case of genus 2. And there's another very important and interesting paper that is worth to mention that does not fit into the previous attempt because the way they do it is different, but it also uses principally polarized abundant surfaces, the one done by Juan Zhang. Well, here, what do we obtain? We obtain an intermediate result between, okay, we would like to obtain holomorphic Siegel quasi-modular forms, but what we obtain are meromorphic Siegel quasi-modular forms, and we can identify where the poles could lie. Yes, could lie. Well, and so our result is a construction of a differential algebra of meromorphic Siegel quasi-modular forms of genus 2 for the full symplectic group. The method is an application of the Gauss-Manning connection in this guy's method from Professor Movasati, and it's essentially divided in two parts. In an algebraic part, we construct the algebraic counterpart of the algebra of Siegel meromorphic quasi-modular forms. Our Siegel meromorphic quasi-modular forms are going to be some meromorphic functions defined on the Siegel half plane. In our case, we are going to obtain first an algebraic version of that without intervention of the Siegel half plane. So how are we going to obtain this algebraic version of both, of Siegel modular form and Siegel quasi-modular forms? We're going to define them to be the regular functions of a moduli space on a subset of the moduli space, on a patch of that moduli space, which has this structure of a quasi-affine variety over C. The differential structure will be obtained by constructing algebraic vector fields on that patch O. That's the algebraic part. How do we obtain functions, indeed, meromorphic functions on H2 on the Siegel half plane? That is done by means of constructing a holomorphic map that will be called the T map. which will allow us to pull back these algebraic Siegel modular forms and quasi-modular forms to modular forms and quasi-modular forms, indeed defined over H2, but we must take out the complement of that set of that O. That O will not be the whole modular space T. We will be taking out some specific part. So we must cut that part out from H2. And well, that's basically everything is almost identified in a work by Clingher and Doran. This method, as I said before, is an application of a bigger project called Gauss-Manning connection in disguise from Professor Movasati. So I'll begin by the algebraic part first. Well, I'm not able to see here how many minutes. Okay, perfect. Let's begin with the algebraic part. The context, the algebraic part comes from the work of Clingher and Doran. Basically, we're going, that moduli space T that we're going to consider is a moduli space of quasi-ample and polarized K3 surfaces. But I'm restricting a little bit more here, and I'll tell in which sense I'm being a little bit more restrictive. So, well, n-polarized K3 surfaces have a parameter space that was everything here that I'm going to say is from the work of Clingher and Doran, have a parameter space that can be identified by this U as a parameter space of some projective hypersurface, which are singular. And these are the hypersurfaces given by the polynomial that's written down there. If you resolve under the condition that those parameters live in the set U that I'm writing up there, you get a K3 surface as a minimal resolution, and this K3 surface has a high Picard rank that is greater than or equal to 17. And well, these constructions come from the work of Clingher and Doran. Well, one way to see the polarization, where does it come from, is to consider what they call a standard elliptic vibration on those K3 surfaces. How is it? This elliptic vibration is obtained by means of, we have here this rational map pi, and this rational map pi is the one that induces the standard vibration. It's very important to know that this rational map pi is a projection onto the last two coordinates, and it induces the standard vibration. And from this vibration, because the Clingher and Doran describe precisely two special singular fibers and the existence of a section, we can obtain, or they obtain, the n-polarization. So they have this theorem that is that under the hypothesis that that note both of them are zero, C and D, the standard vibration has a section and two special singular fibers. The one of the singular fiber has a fixed codiagram type, and this codiagram type will correspond to the array, the curves of the singular fiber, which correspond to a E8 array. And on the other singular fiber, the one that lies over 1.0, the type may vary depending on the value of C. If the value of C is equal to 0, we have that this type is the same as the type of the other fiber. And well, if C is not equal to 0, we have that the type is indeed 3 asterisk that corresponds to E7. For us, it will be important to fix, to consider C different from 0. Why? Because if C is equal to 0, we may have automorphisms of this elliptic surface with which interchange those two, well, at least it seems to me that they may interchange those two fibers. So I don't want that to happen. So I'm going to restrict myself to, well, I'm going to restrict myself to these kinds of polarizations. I'm going to restrict myself to n-polarized K3 surfaces whose M polarization does not extend to an M polarization where M is that lattice. What does it mean? Basically, I'm going to restrict to K3 surfaces of this type where necessarily the parameter C is different from 0. I'm calling those K3 surfaces strictly polarized K3 and polarized K3 surfaces, even though this name may not be good. But okay, so these are the objects of the moduli space that we're about to define. One observation. For strictly n-polarized K3 surfaces, an isomorphism preserving the polarization is equivalent to an isomorphism of elliptic K3 surfaces for the respective standard vibrations. By using this, one can prove a proposition that describes automorphisms of strictly n-polarized K3 surfaces. And they are of this form in the respective singular projective hypersurface. Okay. What's our moduli space S? We have two moduli spaces involved here, one S and one T. Basically, both our moduli spaces S and T will be moduli spaces of n-polarized, strictly n-polarized K3 surfaces complex with some enhancements, with some embellishments. The first one is just to add a non-zero holomorphic two-form. So what do we do? This moduli, the moduli S is a moduli of triples. Basically, what we have here is an n and strictly n-polarized K3 surfaces with a holomorphic non-zero two-form. So we have this moduli space, and it's easy to prove that this moduli space as an analytic space over C is isomorphic, is biholomorphic to this subset of U. And basically, the morphism that you should consider is the obvious morphism, the one that sends the parameter to the K3 surfaces and its associated holomorphic two-form by means of the residue map. The details can be found in the thesis. Okay, so our first definition. What are the algebraic meromorphic Siegel modular forms of genus 2 for the fourth symplectic group? Is just the algebra of global regular functions on S under this identification of S. Therefore, they correspond to this algebra. Next, we have a moduli space T. What's that moduli space T? Okay, the moduli space T, the moduli space S was enhanced with a holomorphic two-form, non-vanishing. What we do now is that we complete the transcendental cohomology. Not necessarily the transcendental, it may be a little bit bigger than that, but we complete we pick a n-polarized K3 surface, strictly polarized, and we fix a basis of its middle rank cohomology modulo its polarization. That gives us this pointwise is a complex vector space of dimension 5. So we have there that basis must have 5 elements, and we ask two things for that basis. That basis must be, well, that's verboten. The basis must be compatible with the Hodge filtration. What do I mean by that? The first element must be in the last piece. The next 4 elements must be in the next piece, and obviously all of them will correspond to the whole cohomology, modulo depolarization, and more importantly, we must fix the intersection product. Well, the intersection product that we are fixing, particularly for a WEC, is this. I must say that if you are working over C, the intersection product, as long as it has those outer ones, the one that is on the first column and last row, and the one that is on the first row and last column, you must always have them, but you may vary what's in the middle. No matter what you put there, if it is a singular symmetric thing, the modular spaces that you obtain by varying those matrices are canonically isomorphic over C. But if you go to lower rings, for example, to Q, you have problems because you must study congruency of matrices. And well, over C, it's easy. Over Q, the modular spaces may not be isomorphic. It depends on the congruency class of this matrix. Well, so our space T, are n-polarized case-free surfaces enhanced with what? With a basis of the middle-rank cohomology modular depolarization that is compatible with the Hopf filtration and which has an intersection product and fixed intersection product. What's okay? I originally gave this definition. Well, Hossein originally gave this definition. The algebra of algebraic Siegel quasi-modular forms of genus 2 is the regular global functions on T, but we are not really going to obtain that algebra. We're going to obtain that over a subset of T. So we're not going to obtain really algebraic Siegel quasi-modular forms. We're going to obtain meromorphic Siegel quasi-modular forms. And we will see why later. Okay. And the projection morphism, the natural projection morphism that goes from T to S and forgets the last four forms of the basis and only retains the holomorphic one, induces a monomorphism in the sheaf of sections, in the algebras of sections. So we can see that one algebra is inside the other. So the classical Siegel modular forms are inside the quasi-modular forms. We will see one inside another under this embedding. Okay, now we aim to give a description of this modular space T on a subset of T. That's basically what we need is contained in the work of Doran, Hossein, Wicha, and Hora. And in the last section of that paper, they give a basis. Okay, let me see if I have this written here. Okay, they give algebraic sections of the bundle that is obtained by considering pointwise these cohomology, these secondary rank cohomology groups modulo depolarizations. I'll describe this in the proof. The work that we need to give a description of a patch of O is basically a consequence of the work in this paper. But we can see that indeed the whole modular space T is a quasi-affine variety over C, but this cannot be seen directly, at least from what I did, because I was not able to produce a basis that works on the whole parameter space. The basis, we attempted to do this with Hossein, but we have some difficulties, serious difficulties. So we could just achieve a description on a chart. But if you want a global result, you can compare this modular space by means of the work of Nikulin, or also by means of the work and Clingher and Doran, to the work of Fonseca, which described that modular space T, but for principally polarized abelian surfaces. There, Fonseca was able to prove that modular space T is indeed a quasi-affine variety over C. So we can move that result to this result by means of that correspondence, but I'm not going to get into detail into that correspondence here. Well, what do I need from the work of Doran, Hossein, Wicher, and Hora? what I need is basically, well, they recompute there a discriminant that also appears in the work of Iguza. And it's important because what we are going to take out from H2 will be basically the zero set of an Iguza cusp of degree 35. And it is like that because what we're going to take out from the modular T will be essentially the zero set of this discriminant. This discriminant, we must know that C divides this discriminant. And this discriminant is a homogeneous polynomial of degree 17 in that greater ring. Well, was computed in Iguza and then recomputed in Dorian. Well, the description, here we have a theorem that is the description of a patch O of T, and we prove that O is a complex quasi-affine variety. This is a standard procedure of the Gauss-Mannini connection in this guy's method. Basically, what we say is on O, that is at the parameter space that we were originally considering, but minus the zero locus of the discriminant delta, we take that algebraic subset O of B. On that subset O of B, Hossein, Durham, but they constructed an algebraic section, algebraic sections on the whole O, not on the whole V, on the whole O, which are locally a basis for the transcendental de Ranke homology, in the sense that is the de Ranke homology modulo the image of the polarization, and this basis is compatible with the Hodge filtration. Well, one thing, very interesting thing, would be to compute the intersection product in this basis, but that was something that we did not do in this thesis, and is a kind of project that I would like to attempt in the near future. So we let O, well, I don't know how to call that, like O special O, to be the pre-image of that O that I was considering at the beginning by means of the projection, by means of this projection, the one that maps the modular space T onto the modular space S. So we take that pre-image, and that will be our O. We're going to prove that O is a complex quasi-affine variety. So what do? Okay, we define regular functions, which are basically the intersection pairing of that frame. Any other tuple of sections comes from that frame multiplied by a change of basis matrix. Therefore, the parameters that we are missing come from that change of basis matrix. We can further suppose that the change of basis matrix, the first element there in row 1, column 1 is 1. Why? Because we have automorphisms of n-polarized case-free surfaces that allow us to scale, to rescale if there is a number in there, because that number would correspond to a multiple of the holomorphic form, and we can rescale that out by means of suitable, for example, in the work of Clingher and Doran, there's the needed isomorphism is described to do that rescaling. So what else do we need from these parameters? From these parameters, we need them to produce us an alpha, which intersection product equal to psi. That's what we are requiring. We are taking an ideal that is generated by those by the equalities in the entries of that matrix equality. And what we conclude that O is a Tsariski open subset of the spectrum of that C algebra. Well, from this previous proof, we conclude what? We have that the global, that the regular functions on O are described by that algebra. Therefore, we have here our description of our meromorphic algebraic algebras. This concludes the constructions of the algebras in the algebraic part. Next, we should address the differential structure. How do we address the differential structure? To talk about that, I must first introduce an algebraic group, and is the moduli space T is related to the moduli of strictly n-polarized K3 surfaces without the information about the cohomology by means of the action of a group that allows us to forget the basis. So basis, there is a group, basically there is a group that acts on the right of the moduli space T that captures all of the information of the basis in the cohomology that we are considering. This group is a subgroup of an orthogonal group. And here's the definition. It must have orthogonality with respect to the matrix psi because it must take a basis with intersection product psi to another basis with intersection product psi, and it must respect the Hodge filtration because we are considering bases that respect the Hodge filtration. In which sense? In the sense that, well, the first element lies in the last piece of the Hodge filtration, the next four element in the next piece, and the whole, well, correspond to the whole cohomology quoted, moded by the polarization. And what do we have? Well, this group acts on the right. We will see, for example, that in the chart that we described, it's easy to see. It acts algebraically, and its quotient is isomorphic to the moduli space M. Therefore, from this, we can give a description, we can give a computation of the dimension of the moduli space T. That moduli space M, by the work of Clingher, for example, has dimension 3. It's easy to compute this group, and this group have dimension 7. Therefore, we see that the moduli space T must have dimension 10. Well, now we consider a Lie algebra that is obtained by means of the Lie algebra of this group, but we add 3 elements. And it's easy to compute that this Lie algebra generated by the Lie algebra of the previous algebraic group with these added 3 elements, it is isomorphic to SP4C. And we denoted it by G. I'm sorry, it may be an abyssal notation because by G one may think the Lie algebra of the algebraic group G. Okay, here I will be considering G to be this generated Lie algebra of the Lie group, Lie algebra of the previous algebraic group, and these 3 added elements, which is isomorphic to SP4C. Basically, what is this Lie algebra? Is the Lie algebra of the orthogonal group. That's all. Because what we are adding are the remaining elements that were taken out by the condition of that the elements should respect the Hodge filtration. So basically, this algebra is SO5C. And it is a more or less well-known result in Lie theory that SO5C is isomorphic to SP4C. Well, the differential structure of the algebra of meromorphic, we are in the algebraic context, Siegel quasi-modular forms. As we said in the introduction, this differential structure comes from 3 vector fields defined on the patch that we were considering, on O, and these vector fields are algebraic and defined over Q. And the way we're going to construct them will be by means of the next theorem. And we're going to construct, indeed, 10 vector fields. Each vector field by each element of this algebra SP4C. By each element of that algebra, we're going to consider an algebraic vector field on the patch O. And 3 of them, the 3 corresponding to G1, G2, and G3, will be these vector fields that I'm calling here R1, R2, and R3, that are also called in the literature modular vector fields. Okay. In the notation of the theorem that I'm going to introduce in the next slide, nabla is the Gauss-Menning connection of the family of the surfaces of the Clingher-Doran family restricted to V. what's V? I'm sorry, recall that we have this parameter space, and from this parameter space, I extracted this further parameter space. Okay? Well, let's return to the proof. Okay. Oh, indeed, the connection that we're going to consider is not over that V, it's over a subset of that V, and it's the complement of the vanishing locus of the discriminant. Okay? Because it was over that subset that it was computed a basis compatible with the Hodge filtration over the whole algebraic basis, compatible with the Hodge filtration over the whole O. Where here's the statement of the theorem. For each element of that Lie algebra that is isomorphic to SP4C, there exists a unique algebraic vector field on the quasi-affine complex variety O, such that this equality holds. What is alpha? Recall that in the proof of the parametrization of that O, we have that the omega was the basis constructed in the paper of Clingher and Doran, of Doran, Hossein, Movasati, Witcher, and Hora. And alpha is obtained by multiplying that basis with a change of basis matrix, and that is the alpha that we are considering here. Well, the proof of this theorem, if we have time, is sketched at the end of these slides. And what I want to observe is what I mentioned just a moment before, and is that the modular vector fields correspond to the vector fields constructed by the previous theorem for G1, G2, and G3. And what are G1, G2, and G3? G1, G2, and G3 are these matrices. Well, by that description, you can see why are they called modular vector fields. They satisfy the definition of Professor Hossein for a modular vector field that I'm not introducing here. There is another theorem that can be proved following the lines of the previous proof, and it is that the classical, we have Siegel modular forms, which in our case will be meromorphic, but we have Siegel modular forms. Then we extend them to quasi-modular forms. How do we characterize the modular forms inside the quasi-modular forms? There is one way to do that, and it follows this proposition was essentially like taken from a paper of Yao, Movasati, and Alim, and there was one for the case of threefolds. Here I did it for this case, and it is a characterization of the classical Siegel modular forms inside the quasi-modular forms as a kernel using the previous vector fields constructor. Here, I'm sorry, I should have said what is that G sub 0 that I'm taking out from the Lie one. In the end, if you are interested, I can write what's that G sub 0 that I'm taking out of that intersection. It is basically the matrix which has a 1 in the first row and first column, and a 1 in the last row and last column, and the rest of numbers are 0. Okay, so here we achieve the construction of the algebraic part of the algebras of meromorphic Siegel, quasi-modular forms, and modular forms. Its differential structure, that the one we're interested in is the differential structure that comes from these three modular vector fields. So the algebraic part is concluded here, at least what we were able to do. Then it comes the transcendental part. We need to construct that tau map, that T map. How is that T map constructed? Well, that T map is constructed by means of considering periods. So first, the classical period domains or Griffiths. Let us observe that the classical period domains of Griffiths contain the periods of the holomorphic forms. What Movasati does, and basically here we are applying all works of Movasati that is part of his project, he considers a generalized period domain. In which sense it is a generalized period domain that he doesn't just keep the information of the periods of holomorphic form, but he keeps the periods of the entire de rank homology. In our case, will be of the entire de rank homology molded, quoted out the image of the polarization. So first we need to describe how those matrices behave. And this is simple, the RAM thing. This is not hard. And the first proposition is that if you take an impolarized K3 surface and you consider a basis of the integral, call it transcendental homology, with intersection matrix equal to the inverse of the previous matrix that we were considering, that intersection matrix is just a matrix with an anti-diagonal of 1, 1 minus 2, 1, 1, the inverse of the upside, of the psi side. Well, how do we define the period matrix associated to that? And hence, impolarized K3 surfaces. With that basis, as usual, we consider integrals of the form over the homologic class. Then we have a description of some things that period matrix satisfies, which are an easy computation. The first one is just a computation with the rank homology, and the second is a consequence of the Riemann bilinear relations. What we do next? Therefore, we see that we collect these possible period matrices into a manifold. That is what I call the manifold of period matrices. Then observe that, as usual, if we want to define that period map, in this case, we would call it a generalized period map. Why? Because we are considering not just holomorphic form, but forms for the entire rank homology. We would have the action of the monodromy group. That is what I call their gamma sub z. So, in general, to define a generalized period map, we must take into consideration the action of the monodromy. That is what is done there. It can be proved as a consequence of Torelli theorems for polarized K3, of Torelli theorem for K3 surfaces, and a little bit computations, that map is indeed a biholomorphism. Therefore, we have, at this moment, a biholomorphism. Remember, we are trying to construct a T-map. What is a T-map? I'm sorry if I'm going quite fast. A T-map is the following thing. A T-map will be a map from the Siegel half space to our moduli space, which is holomorphic. Why do we want to do this? Because we want to pull back all those algebras that we constructed as algebras of regular functions on T, or regular functions on a subset on a chart of T. We want to pull them back to holomorphic functions on the Siegel half space, possibly really meromorphic with poles along a set that we will describe. So we're trying to construct this T-map. The first step in the construction of that T-map was the definition of the generalized period domain, which is a biholomorphism. Next, we define a tau map. What is a tau map? A tau map, basically, that H2 modulo monodromy contains the information of the periods of holomorphic functions, of holomorphic forms. So it basically contains the information of the complex structure. And we want, with this information of the complex structure, we want to construct the whole Hodge structure. So a tau map is essentially that construction from the complex structure, the construction of the entire Hodge structure. in a holomorphic fashion. And how did we achieve this? Well, we basically, the tau map is very easy. It's almost immediate to define for principally polarized abelian surfaces, and in general, principally polarized abelian varieties over C. And it was done in that paper that we refer as the first paper, well, quasi-modular, Siegel quasi-modular forms was mentioned. It was done in that paper by Hossein in 2013. So what we did was to pick that tau map, and we passed that tau map by means of a work of Nikulin to our context. So basically, well, it was not created very originally. It was a mixture of works. It was mixing the work of Nikulin and the work of Hossein and its collaborator, and we were able to arrive at this tau map. This tau map, it behaves well because if you, well, it gives you in the first row the periods of the original period you are considering in H2. You can see them there. There is a 2. You say, well, there is a 2. It doesn't fix. There is a 2 there because the lattice that we are considering is psi. That 2 can be explained, and it's not such a problem to explain that. That 2 comes from the following, that we consider in the definition of the modular space T, this matrix. And the 2 comes from the change of basis from the lattice induced by this matrix to the one induced by the inverse of this matrix. That is the same matrix, but with a -2 in the middle. So basically, that 2 comes from a change of basis. If you change of basis, you must multiply the middle by 1/2, and you get the classical period. So this tau map is holomorphic, and it's all we need to put everything together into this composition that comes from H2 to tau, and allows us to pull back those. I'm sorry, I have connection. Everyone's listening.
Yeah, go ahead.
Okay. So we put everything together here: the tau map, the inverse of the period map, well, the natural projection, and we get the holomorphic map that we wanted. And what happens here? Remember that on all we were taking out the discriminant. The pullback of that discriminant by means of the Clingher and Doran Weck, that discriminant will be pulled back to the Siegel cos of degree 35 to the square. So we are pulling back the zeros of that cos form, and they correspond to what I'm writing here. So what we are obtaining in these are algebras of meromorphic functions with possible poles along that set that is the diagonal equal to 0, or the anti-diagonal equal to 0, or the diagonal identically equal, both elements. Well, this tau map, we can consider it like the functions that go. This tau map can be considered having. Well, what I mean is that how do you say that? The coordinates of this tau map into tau. This tau map is defined on H2 and goes to T. So it has coordinates with respect to the coordinates of T. We may restrict to a set where we have coordinates. And it has 10 coordinates. Those 10 coordinates are solutions of the vector fields that we introduced before, that are the modular vector fields. And ABCD, recall that we had ABCD. The pullback of them was computed by Clingher and Doran, and they correspond to the generators of the Siegel modular forms of even degree. So we have, as a pullback, we have modular forms and quasi-modular forms. And this is a conclusion of the transcendental part. In this way, we pull back the algebraic Siegel quasi-modular forms to Siegel quasi-modular forms as meromorphic functions. Well, next I have the proof. Of two theorems are basically computations, and the proof of the that the period map is a biholomorphism. There is also a computation and using some consequences of the Torelli theorem for K3 surfaces that I think that since I'm completing now the 15 minutes, I'm not going to expose. So here are the references that I used for the slides. And thank you. Now I'm open to questions.
Okay, thank you. You saved us 5 minutes. Okay, thank you, Walter. So now we come to question session by the committee members. I will start from from senior to junior.
I'm sorry, I didn't understand.
I'm not talking with you. I'm talking with members of the committee. Alcides?
Hi.
Alcides, tem alguma pergunta? Se quiser, pergunta.
No, I have no question.
Okay.
But I think the thesis is interesting, but I'm not familiarized with this type of stuff, but very interesting.
Anyway, if the differential equations are one were explicit, it would be much happier. They are just exponential or no. Okay, Adrian, do you want to make any comment?
Sure. Very interesting work. I'm actually looking forward to see how this procedure perhaps works beyond the SP4. But I like the thesis. I read the thesis, and it's very nice work.
Actually, I told Walter that maybe these towers of K3 surfaces that you always have worked out.
Yeah.
Try to write down for all these towers, but the issue is explicit.
It probably will get more complicated as you go, but given the technical difficulties that Walter overcome, maybe it will work.
Okay. Okay. So let's. I told from senior to junior. No, maybe Younes. Younes, you are in the. I think you are younger than Jin. Or you are older than Jin.
Okay, thank you. Thank you for trusting me also for being referee. Okay, I talked once with Walter. I'm going back to the talk that I had with him once. So because you are giving three vector fields R1, R2, and R3, okay?
Yes.
And then you are defining the space of algebraic Siegel modular forms. But in the definition that you are giving, you are not mentioning that this algebra should be somehow solutions of these vector fields R1, R2, and R3. And what I expect, this algebra should be solutions of these vector fields. I'm right, or?
Oh yes, that's not immediate. We must make an argument about because the way we are embedding H2 into the. In some sense, we need to prove that these vector fields are tangent to the image of the tau map.
Exactly, because you are defining the space of algebraic Siegel modular forms as a regular function on T. All the regular functions, if I understood good, and then you give simply these vector fields, and you just say that due to definition of Movasati, they are modular vector fields, and then you don't say that exactly the solutions of these the space generated by solution of this vector field that is exactly what I expect is that. And one more thing.
I don't know how to. That is exactly the solution. The space of solutions of that vector field is exactly those ones. I don't know how to put that, but I can prove that they are solutions.
This is why I expect that.
Yeah.
Because in the case in the classical example that you give of the case of Ramanujan vector field, then the solution of Ramanujan vector field that generate the space of quasi-modular form. So here you have three modular vector fields. So the solution should generate the space of this algebraic Siegel modular form that you are defining, and I expect this one. And one more thing, I think you can associate maybe for the future works to any Ri, let's say R1, R2, or R3. You can associate to any of them one SL2C Lie algebra structure. And then using this Lie algebra structure, it will be simpler to identify quasi-Siegel modular forms from Siegel modular forms. And I think maybe in the future, maybe we can talk more, but I'm pretty sure that maybe you can do this work as well. Anyway, I like the word, so it was honestly it was difficult for me to read it, to follow it. It needs to be written better, but it is very interesting work. Okay, I'm done.
I would like to thank you a lot, Younes, for your commentaries and your reading. And yes, thank you for. I don't have a complete answer or no answer to that, but I think I will be working on those things in the following months.
Maybe Walter, at the end of December, you write this when you take these holomorphic objects, then they are the solutions of these three vector fields.
Yeah,
you write it in as a proposition, and the proof is easy. I mean,
no, that proof is not hard. But how do you prove that they are the whole set of solutions?
No, I think what the point is that maybe we can discuss later about this.
Yeah.
Did you try to find the solution in terms of Q expansions or things like that, or not?
No, I didn't.
Okay, so maybe it works. Anyway, I have more comments. I will send you later.
Oh, we could talk, and I will.
The thesis.
We'll be really glad to hear them, to receive them. Thank you.
Okay. Thank you, Younes. So we go to Jin. I think I'm following the right order. I don't know.
Yeah, I have a question. I also interested in the connection of T-module space in your case and the T-module space for genus 2 curves. Is there some reasonable map from that T-module space?
Yeah, I think that by extending on the work of Clingher and Doran on their paper, because they give, let me think, they give a way to produce something that are related, that are invariants of those genus 2, where Clingher could correct me, of those genus 2 curves that are the Clebsch invariants, a way to produce them from the ABCD that I'm considering here. So I think that, well, this would create a connection of the transcendental period domains, a map between the transcendental period domains of what you did with Hossein and what is done here. How does it extend to the algebraic part? Certainly at this moment do not know, but I think that the essential information must be contained in the paper of Clingher and Doran.
Yeah, I think this is when you have to understand this Shioda-Inose correspondence that
exactly. Yes.
Adrian and Doran they talk in their article, and to push it up to in the level of differential forms and periods. Exactly. And but this is something which is not done yet.
Yeah, because I'm wondering, is there some smallest T-module space factors through if you have some Siegel module form?
If there are some what? I'm sorry.
Smallest one. Is there some universal T-module space cover all the Siegel module form?
Honestly, do not know.
For example, in the final, do we impact for any transcendental map from some Siegel alpha plane to T-model space will factor through some special T-model space or not?
Okay. Yeah. Well, I certainly don't know, but I will be thinking about that with Hossein the following time.
Well, my impression is that the answer is not, but one has to think.
I don't think you have a universal one, but maybe, yeah, I don't think.
Anyway, there are a lot of choices that one has to make. I mean, for example, the Soika, this psi matrix and so on. But at the end, all the theories are the same up to some isomorphism if you change all these choices.
Because my question, in fact, is does module form really we can reconstruct some Minkhouse structure from this Siegel module form?
Well,
yeah,
I must think of that.
Yep.
Okay. Okay. Thank you.
Okay.
Thank you, Cao.
So, sorry, Roberto, I put you in. Well, actually, not sorry, because you are I considered you're the youngest member. Actually, the suplente. But anyway, do you have any question?
No, just one comment about this question of Younes. I think there is something that you haven't pointed out in your definition of this modular vector fields, because if we want this image of the T map to give us the solutions of these differential equations, the minimum that you need is that these vector fields are tangent to the image of the T map, right?
Yes, the minimum.
And that is a two-dimensional variety.
Yes.
So this space is two-dimensional, right? There are two vector fields that you're looking for, not three, right? One of this three-dimensional space is like.
I'm sorry. Why is it a two-dimensional variety?
The image of H2, right?
It's three-dimensional, no?
No, it is three-dimensional.
So what's sorry? So I had I made a mistake.
But no, I understand. It's three-dimensional.
I
They should correspond to three of them.
Okay. So it was my mistake. Okay.
No, thank you, Roberto.
Okay, Roberto, that's all. One more, something more?
No. I mean, well, just I think that as Younes said also, yeah, the work is very, very nice, very interesting. But I really believe that it deserves to be better written.
Yeah.
Yes.
It
Thank you for your comments.
For me to read it also.
Okay. I think we are done. Anderson, I think we have to stop the recording now. And then
no, I'm going out.
You have to go out. No, I mean. But there is a Walter.
Ah, boy.
Walter. Okay, Walter. Congratulations, you are approved with some small condition that is still you have to improve the text until, let's say, mid-January. And
Thank you very much.
The idea is that to give a version of the PhD thesis to the admission office, which is much more appropriate for publication and so on. In the meantime, if you want, I can help a little bit to write article. Yeah. Parabéns.
Thank you very much. Obrigado. Gracias.
Congratulations.
Congratulations, Walter.
Okay.
Obrigado, Younes. Gracias. Muchas gracias. Thank you very much to you all, and thank you very much for taking the time to be here and to listen to me.
Okay. Tá bom.
Congratulations.
Tchau.